So thanks for coming. My name is Christian. I'm presenting some work we did on protecting databases with syntactical analysis of SQL commands. So that's called protecting databases with trees. This doesn't work. So my primary profession is I'm a researcher at the artificial intelligence group of the University of Dortmund. And basically, I'm studying the use of machine learning methods and artificial intelligence methods, like data mining methods, for machine learning, for web security. As a hobby, I'm developer of several projects, all affiliated with mod security, with the mod security web application firewall. So I have some stuff on my web page, jwall.org, which is some log file aggregation management stuff and some web application policy compiler and so on, and this is what I do in my spare time. So this talk is not touching anything of that. This talk is about first the threat of SQL injections. Is that still a valid threat? Then I'll try to give a picture on where we can fight SQL injections, and then I will start diving into how we thought SQL injections might be fought at a good place. So I'd like to start this talk like every good SQL injection talk. And every good SQL injection talk probably starts with this. And I guess, who does not know this? Okay, at least one. So basically it's just a student typing in his student name, and he types in Robert apostrophe drop table students, and that gets inserted into the database, or gets inserted unvalidated into the web application. It finally hits the database, and it inserts some record and drops all the other records as well. So this cartoon is about 5 years old, and if you just attended the other talk beforehand, you notice that SQL injection is about 13 years old. So it's pretty amazing that, so the first question which arose to me was, is it still a valid research topic? So is it really necessary to focus on SQL injections? This was the web hacking incident database, which is a record of all web hacking incidents which have been becoming public, and this is just the first half of June this year. So there was this Sony breach, Sony Europe breach, some DOS attacks, an FBI website was hacked, and some more stuff. And if you look at the types of attacks, then there's a lot of SQL injections involved in that. And if you just display that, then there's almost half of the attacks which have been carried out against web applications have been SQL injections. Most of them are just easy, and they are especially easily to be automated with a lot of tools. Imperva has a trend report they give away every month, I guess, and there was one, which is number 4, in which they monitored like 30 web applications, and they were just checking what kind of attacks have been raised against these. So they found out it's like 71 SQL injection attempts on average per hour. They have like 800 to 1,300 injection attempts at peak times, and most of these have been carried out by highly automated injection tools like SQL Map or Have. Has anyone experienced with SQL Map? So, and the others, have the others ever heard of SQL Map? Who has not ever heard of SQL Map? So this is quite a nice tool by Bernardo Namele and some other guy, and it just checks your web application for injectable parameters, and once it found something, it gives you a complete shell of your database through the web application. It does encoding, it does tempering, and does try to avoid detection by numerous mechanisms, and it's pretty good. So another trend report was about the topics of hacking forums, so they just checked on online forums how about what types of attacks do hackers discuss. And you see again that SQL injections, that the yellow one, is almost 20%. Then when I entered this conference, I checked my Twitter account, and I just use Twitter as a good source for getting notifies of new attacks. And this is what I've just found yesterday, and that's a week old. So there was a SQL injection in a C# environment, and there was the story behind this is about some developers who just coded the C# page, and some of their stuff didn't work. So they found a flag which says validate equals true or false, and they just turned off the input validation with that, and then their code worked, so they were happy, and this is the result. So if you just have a look at the top 10, OVA's top 10 list, then SQL injection is on that list for a long time. And also, if you look at other institutes which compile such lists, then it's like, this is the SANS Metre top 25 programming errors. So there's also the improper neutralization of SQL elements is just a high impact topic. Guess what? It doesn't always hit web applications. So this is Android, and data is stored, any data is stored in databases, also SMS. So there was a SQL injection in an SMS gateway, so you could just use your mobile phone to inject SQL commands into the database of your SMS gateway system. So it does not only affect SQL injection. So what makes up SQL injection? Basically, what we have is this situation. I guess this is what most of you guys have at home or at work. So we have some web server which is serving URLs, and once in a while there are some URLs, web requests hitting your database, hitting your web server, and your application is somehow executing a SQL command back on the back-end database, produces some results, and delivers that to the client. So the question is now, what makes up a SQL injection? Basically, there's two things involved. First, the attacker has to insert some payload, some SQL payload into the web application. Okay, so this has to be inserted somewhere here, and it has to reach somewhere into the web application logic. And the second condition we need to have is we need to have this SQL injection piece have to alter or modify the SQL statement that is to be executed. So if we just insert some union select login password from users, and if we do this correctly, and the web application is vulnerable to SQL injections, then the database statement is not only select title and abstract from docs, but it's a union of the first select and the result of the second select statement. So this is basically the core idea of SQL injections. So where can we fight SQL injections? And if you attended the last talk, then you should be aware that the first step you have to do is you have to fight SQL injections within your web application code. So if you have any chance to access that code, and if you have some, you didn't outsource your application, but you write your application yourself, then this is the first step you need to take. The second one, which is usually done, is within the HTTP traffic. So you employ like a web application firewall, intrusion detection system, or something like that. These are all in front of your web server or in front of your web application, and these check for known SQL injections. And the last part we can do is, and this is what I will focus on on the second half of the talk, is we can fight SQL injections within the executed XML code. So this is the third location where we can fight. Having a look at the first one is, so they're pretty good guides for like code review and do train your developers, raise awareness of SQL, of the danger of SQL injections and stuff like this within your development team, do penetration testing, do risk management. Okay, we just heard, forget about risk management on the other talk, but still that's one of the approaches which are recommended. But this is just the best thing to do in the first place. So what we can do here is we can use prepared statements. Prepared statements have been around for quite some time, and there are prepared statements for like almost every language. And what they do is you don't directly insert user input anymore into the SQL string you want to execute. What you do is you give that template string to the prepared statement and then make the database driver escape all the special characters, so there's a safe container so that the attacker cannot break out of the statement. This is good, and I believe that almost if you don't hit a bug in your database driver, then you will be probably almost 100% sure about SQL injections by just using prepared statements. However, you can also do wrong with with prepared statements. So if you just use prepared statements and concatenate the user input into the prepared statement, then you don't have any benefit of that. So this is about developer training. And so I would just close this, have a look at the code section now, and now we moved on to some different part, which is intrusion detection and prevention. And this is my favorite site of Damiano Balzoni of the Focus IDS mailing list, and this says just all this stuff about intrusion detection and intrusion prevention is just a big attempt to patch bugged systems. So in the first place, we need to have a patch for the system itself, for the application. And this, by everything we do now, is just a helpless, like crying for help, maybe. So what do intrusion detection systems do? Some things like PHP IDS or Snort or web application firewalls like Mod Security and some vendor-specific stuff have been promoted to check the web traffic against which hits your web application. And basically what they do is they check for keywords of SQL commands. So they check the user inputs and just ask themselves, I have a list of known SQL injections or known SQL keywords, and is there any of that keywords in my user data? And this is like a pattern matching approach, and this is employed by almost all web application firewalls and intrusion detection systems, like the Mod Security core rules, the IBM web application firewall, Imperva, SecureSphere, and some others. So this is basically the approach they do. And it's not just keywords. Most of the time it's complex regular expressions. So this is a regular expression of a mod security rule which helps you find SQL injections in your input. Now, corresponding to that is an email on the mailing list asking, okay, I have a trigger of that regular expression against that token. So there was some cookie. And basically, the regular expression just found this two characters, or. Woo! That's a false alert. So it's really hard to write good rules. So and you have to take care of a lot of things, and we'll see in a minute. So some of the web application firewalls try to replace known keywords. For instance, the following one would this one would probably end up as a database error. So if once the web application starts removing a keyword, we end up with a much finer statement, and this is a valid SQL statement. And if your application is prone to SQL injection, that will hit the database. There are some great articles. One is a presentation by Johannes Dase from the Ruhr University of Bochum, which is somewhere near my place. And there's another white paper from the CWH Underground, crew, they just send out a list of how to evade detection of intrusion detection and web application firewalls. That can be done by encoding, by obfuscation, or by HTTP parameter pollution. And I'll give examples for that in a minute. So, easiest thing is some web application firewall just didn't do WURL encoding. So they just used the data and just URL decoded the data once. And if you just do this, then you will end up with this. And if your web application itself does WURL encoding, then the application will be hit by this. And this again is a valid SQL, and that can be hit your database. So that is very easy, and I guess most of the WAF vendors have fixed that problem. So what about other encoding stuff? What about base64 encoding? So if you run an ASP application, there's some variable I was aware of. It's called view state, and it's somehow, maybe correct me if I'm wrong, I'm not an ASP programmer, but view state is just some variable for keeping the client state. And you can also, and this one is base64 encoded and changed between the client and the server. So now you end up with this. How should your web application firewall be aware of that? So you have to configure your web application to actually decode stuff in the right decoding. Because if you decode that, then you have, for instance, a variable, something like, or 1 greater than 0. This may return, for instance, more data records than you want to expose to the user. Then there's comments. For instance, MySQL allows numerous different types of comments. For instance, from the hashtag until from the hash character until the end of the line, from the -- until the end of the line, C-style comments, and some others. And you can try to obfuscate your injection payload by using comments. This, for instance, is completely validated by a SQL command for MySQL. Now, this one is one of the examples of Johannes Dase to evade detection of a mod security core rule set. And if you just decode it, then this is a mixture of hashtag until the hash character until the end of the line comment mixed with a C-style comment, which has no effect because MySQL is just ignoring everything after that, and so on. So you try to obfuscate the SQL command in a way that the patterns of your web application firewall or your intrusion detection don't catch that anymore. Then you have MySQL special comments, which have special syntax with an exclamation mark just for running specific code only on specific versions of your MySQL database. And this can be used for probing the MySQL version you're trying to attack and so on. And there's a bunch of that to evade mod security core rules and the web application firewalls. That's a commercial one. And so this is basic. This is pretty basic, or 1 = 1. So it's pretty basic to just use an always true condition and inject that into your SQL command to return more records than you are about to allowed to see. And one thing you could do is, if you just start with or 1 greater 0 or 1 = 1, you can start obfuscating that. So 2 times 3 is greater than 4. That's a true statement. You can use MySQL variables to check. You can just use MySQL auto typing. So this is a 1. This is automatically typed to converted to true, or auto casting. This is casted to true. And you can run any type of mathematical functions. So if you round p by 1 and add like 2 to that, then you end up with 5, and this almost for sure equals your major version of MySQL database. So this is a neat trick to just evade pattern detection. Another thing which is really cool is, if you just specify a single parameter more than once to your web application, then typically different web applications will behave different. For instance, in PHP Apache, you will just return the first parameter, okay? This is what I would have expected and what most of people would have expected. If you run ASP.NET on IIS, then the parameter values get concatenated with a comma. And this is pretty handy, because if you start this and you're running ASP web application, and you just for safety started to set up mod security in front of that, then this will be the view of mod security. Okay, you can just start throwing your patterns at that, and maybe you just don't catch that, and it ends up in your database, in your web application backend, concatenated with comma, so it's a neat and perfectly fine SQL command, inject, which is not really visible there. So this is an easy example, but you can obfuscate all that with commas as well. So just start an opening comment here and a closing comment here, and this gets concatenated, and you can try to evade your web application firewall. This is idea is called parameter pollution, and this has been successfully used not only to evade mod security, but also to evade the IBM web application firewall and Imperva secure sphere. So my point here was just to emphasize there's a lot of things you can do to get around detection of patterns. And this is just obfuscating. So the big question is how to evade the evasion. So we cannot just use plain patterns anymore. We need to have a way to somehow see the data in a plain way, in a normalized way. And we do this by moving to a different perspective. So we talked about the code security, we talked about intrusion detection at the HTTP traffic, and now we're moving to the database. And there's some benefits we get from this point of detection. First, any encodings which have been used by the attacker have been decoded by the application in the way that that you programmed your application. So second, there's no more mangling done. So the database statement that arrives at this place is not modified anymore. There's an exception for that, so it's internally modified by the query optimizer of your database, but we can just ignore that for a moment. And the fact is that any of the attacks I presented, like any of the encoding attacks, don't work at this level. So you're free. The attacker can just use tons of encoding stuff and encoding tricks, and it won't trick the detection anymore because it doesn't apply here. So recall what a SQL injection is made of. So the SQL injection needs to modify the existing statement, and the modified statement needs to be valid SQL code. There are some, it doesn't have to. Sometimes attackers can also gain information from database errors, so it doesn't always have to be valid SQL code, but we just stick to that for a moment. So in this case, we have select title and abstract, where text like drop table students. So is that a valid SQL injection? And I'd like to ask you, because we had this discussion yesterday. So would that be a SQL injection or not? Okay, and if that's a free text field, then that's a valid statement, right? So it's legal statement, and this one would be, okay? So this one would be, it meets all conditions, it has some SQL commands injected, that's the union select, and it has altered or modified the structure of the SQL statement. And the thing I was thinking about is how can we capture these modifications? So in theory, SQL is a highly structured language. So SQL statements can be passed into an abstract syntax tree. This is what the database does. And the abstract syntax tree is a nice representation or normalized representation of your SQL command. So if you have a look at that, this is some statement. And this is the abstract syntax tree. This is like an idealized one, so there's some more. If you just have a look at the database itself, then there's some more stuff attached to each node. But we start with a select node, then we have a from list, and the from list just references a table, which is docs. Then we have a result column list, which is title and abstract. So these are result columns, and these have like two columns, or column references, and these are referencing some column names. And then we have a where clause, and the where clause is also in a tree structure. So with that in mind, we have a look now at, so we have this kind of structure for SQL injection and for normal SQL command, and now we want to have the effect of a SQL injection regarding that tree. So basically, if you just take that one, then the attacker is basically, and that's the goal of the attacker, he's adding a lot of nodes to our tree, right? So we start up with all the green one, and all the red one is all the stuff that is added to the statement in the tree, or to the tree of the statement. It can be two trees as well. If we have a look at the little Bobby tables from the very beginning of the cartoon, then there's just a semicolon starting a new table, a new command. So we have some legal statement with probably some invalid values, and we have a completely different and completely disjoint new tree. And there has been some work on that by Gregory Bührer and others, and what they did was parse tree validation to prevent SQL injections. So they did notice that that the injected snippets changed the overall structure of the query tree. And what they did is they tried to compare the different trees before and after the insertion of user data input. And they had some implementation called SQL Guard. I had a look at that. I had a look at that, but it didn't work out for me. And the worst downside of this is it needs a change of the application code to use that before and after insertion of the user input of your SQL statement. And here I do have a gem for you. If you need to change the database, your application code, for God's sake, forget about this and stick to prepared statements. This is my first rule number one, which we had in the beginning. The best place to fight SQL injections is to secure your code. So if you have to touch every place where you are using SQL commands, then just use the correct way of using prepared statements, and you're probably safer than using that solution. So back to the trees. What properties of the trees can we monitor to detect any structural changes? So we have like two trees. The left one is the regular one, and the right one is the injected one, okay? And so we can, for instance, have a look at the number of inner tree nodes. All the blue nodes are inner tree nodes, and on the left hand, we have 9 inner nodes. On the right hand, we have 15. We can have a look at the leaf nodes. On the left hand, we have 6 leaf nodes. On the right hand, we have 10. And of course, we also can use the height of the tree. So we have 4 versus 5. And now we check how does this scale to all the obfuscation an attacker might do if he wants to evade detection in the first front layer, like in pattern detection. So an attacker might just replace this SQL or 1 equals 1, this always true statement, and tries to obfuscate this by using round P and round PI and that kind of stuff. So what this ends up in is this statement all alone just creates a new tree. And just imagine this is 1, 2, 3, 4, 5, 6 inner nodes just added by this obfuscation. So in this way, the more the attacker tries to obfuscate, the more he changes the tree. So just imagine, this is an always true statement. Just imagine how large the tree is for that injection. And this is just a subtree of the one where it's inserted. So it's not like 5 to 6 anymore, it's like 5 to 65 or something. And the question we asked was, how can we use this to somehow detect attacks in our application? So we started off with a very simple Java web application. And because I didn't have access to any production systems which allowed me to access the database log files. And so I needed to have some sort of proof environment. So what I used is, I used a MySQL backend. It's highly vulnerable to SQL injections, and it allows to specify a small, simple mapping of URLs to SQL commands. Along with that, I can access this web shop and log all the statements and have a nice data aggregated. So this is how it looks like. This is the typical setup. You have some URLs, and these are mapped to SQL statements. And then you can call all these URLs, and you're creating sort of a baseline of your shop and how it's used. So we generated some normal workload, and then we attacked the shop with SQL map just to see how the difference is. So we ended up with about 6,000 6,200 SQL commands, and about 150 of them have been SQL injections using the SQL map attack tool. And now if you look at the distribution of the number of inner nodes versus the number of total nodes, then you'll see this blue dot is the single statement in a not injected way. So as soon as we start injecting, or SQL map starts injecting, the SQL statement is modified and it's spreading all over just because it has more nodes in it. Okay? There's a special one which has like 200 nodes over here, and this is just all the statements which did not validate against the parser. So these can be just easily attacked because they're just not valid SQL commands. Okay? And to make that a little bit more visual, I just added some jitter, because the small dot on the lower end is not just one dot, it's just a lot of dots. So we added some random jitter. So from a machine learning point of view now, what would you do? You would want to just cut off all the attacks. And this is what we did with some magic. So what we would like to have is some sort of binary classifier, some function, a linear function, which just decides whether whether a statement is on the left-hand side, on the good side, or on the bad side, just using this node count. So this is what my primary job is at Artificial Intelligence Department. So we're looking for simple basic binary classifier, comparable to naive Bayes or something like this, which you use for tagging your spam mails. And we split up all the recorded data into one training data set and a test set. On the training data set, we just trained a classifier. And then on the test set, we used the classifier to test whether this is good for detection or not. And it turned out that it didn't work very well in the first step. So what you see here is, this is the number of this is the reality, and this is the prediction. So from all normal queries, all normal queries have been correctly identified. Okay, so we have no false positives. But there have been like 21 queries which have been sent out by SQL map, which have been classified as normal traffic. So that would be like 21 missed attacks, and this is not what you want, right? So we're fine with that, but there's work to be done on that side. So we had a look at this, and in the first experiment we ran, it was like we were using the user agent field of SQL map just to identify attacks and normal queries. And it turns out that SQL map also sends normal queries just for probing the application, just for figuring out which is a dynamic parameter and which parameter changes the results, just to check which parameter can be injected. So we went through all these 21 manually, and they were all clean statements, so there's just not an attack. We created a second data set, and this time we had like 1,200 statement or queries, and all of them were have been perfectly separated just by counting the number of nodes. Just a note here, and this is just observing a single statement. So that was just more of a proof of concept. Is can we, for one statement, can we just detect attacks or modifications of that statement just by using two features, the tree node, the node count, the inner node count, and the total node count. So this works for single URL, but who does run a web application of you with a single URL? Nobody? I'm surprised. So what happens if we just use the same setup for all queries? So we just used all 6,251 queries, and we wanted to have them classified with a classifier, and it turned out it didn't work. So there's just too few information in just using the tree count, the tree node count. So if you just paint that, then you see that there's some red ones which are modifications of these, which are interleaved with other legal statements. So just using these two axes is not enough for classification. But we have the power of trees. So so far we just used the height and the number of nodes in a tree, but we can do some more. For instance, if we use this tree of a SQL command, then this is the syntax tree, and we can derive all the edges of the tree. For instance, we start with some imaginary start node, and start is derived to select is derived to result column list, to result column list, to from list, to where clause, and we can use all these edges. And that way we can map the tree into a high-dimensional feature vector, into a vector space. So we just, for each statement, we created the parse tree, and then we just counted how many edges do parse trees have in common, and this ends up in a high-dimensional tree. And again, this is the same concept you everyday use in your spam detection mechanism. So this is just sort of a word vector presentation. And it turned out it worked pretty well. So we just ended up with almost all 6,000 statements being perfectly classified. So we're still missing 11 attacks. That's bad, especially since they're attacks. So that's just the learning algorithm we used. So we just had a look at what went wrong. So this was one of the attacks which have been automatically labeled as attack by SQL map, so just by the user agent. And you would agree to me that this is a valid statement, right? So it was just not an error by the statement, by the classifier. It was just incorrectly labeled by me as an attack. It's just a probe of a query. So you don't want to have that as reported as attack. So the classifier was right. This is another one, and you see it looks like an attack, and almost every web application firewall would have complained it is an attack. But in fact, it doesn't alter the statement because it doesn't break out of the string apostrophe, right? So that's not an attack, it's a legal query. So once we corrected the errors statements, we reran the experiment, and it showed up that with a high dimensional vector space, we could perfectly separate all the attacks from the normal queries. As a classifier, we used a support vector machine, and this is like details about the algorithm. So what about a real application? And this is a good question. So the application we tested this on was like a demo application, and it's sort of very small. If you have any interest in validating this on your product, just send me your database log file, and I will be happy to have a look. Probably you won't. Yeah, it's hard to get a productive environment to test this on, but what we did is we checked out typo 3. Anyone using typo 3? So that's a content management system which highly relies on SQL queries, and basically typo 3 does use the MySQL database for everything, for caching, for like everything. And we had like 1,000 queries of in typo 3, and we just changed these queries manually to create like 15 artificial attacks. And about 90% of those have been detected perfectly. But there's still like 10% missing. And our impression is that this is just because we had 1,000 queries which have been created in the log file, but typo 3 itself is using like 500 different types of queries. So it's really hard to distinguish between all these queries with just that small amount of training data. So what we tried to do was we tried to use or get somehow an impression on how this relates to typo 3 as well. So what we used was we tried to get a visualization of your database use. So this is typo 3. I guess you never had a look at typo 3 this way. Basically, this is the algorithm behind this graph is just it uses the query tree to compare the difference between queries, and just starts grouping similar queries into blobs. Like you see that this is a blob of statements, this is a blob of statements, and if you inspect these, then you see that all these are the statements which are using like the select statements for logging in users. These are page caches. This is all statements doing some like user settings or something like this. So that makes sense. That was just for validation that our approach wasn't that bad. You see that there are some isolated axes, and these are all the 15 artificial attacks. So these have not been related to any of the other attack groups, other SQL command groups, with one exception. So here we see that this is a SQL statement, and this is a modification of these statements, and this is again highly diverse compared to the group of statements. So this is some evidence that this distance measure on trees is not a bad idea for doing so. We're still investigating on that. So basically that's it. So as for a summary, we as take-home messages, my take-home message is like a successful SQL query needs to alter the statement which you already have in your database somehow. The syntactical approach of analyzing SQL commands on the back end for detecting SQL injections is pretty promising because it escapes any evasion techniques an attacker might employ to evade your pattern detection. The vectorization of trees has been shown to show good results on machine learning, and still there's room for improvement, especially on more validation on real-world applications. And yeah, the last statement is creating the parser, SQL parser for SQL statement is like almost the hardest part of the whole project, or has been. So just some, if you're interested on some comments on that, and like in theory, parsing SQL should be fairly easy. So there should be some, yeah, I will hit the 5 minutes. Thanks. So in theory, there should be a grammar for your database, which defines all the valid statements of your database system. In practice, and you can use that grammar to automatically generate the code of the parser. In practice, creating the parser, like doing the machine learning, is peanuts over creating the parser. I had a look at several database systems. First, I had a look at the MySQL code. So my first approach was, okay, there's open source databases, I can just use their parser. No. First, it doesn't really externalize, so you cannot easily access the parser. It is very tightly hidden deep into the MySQL database. And it's not easy to get the parser into creating a parse tree. So you cannot really easily access the parse tree for analysis. And this is where you find the parser of MySQL. And who's using MySQL? Anyone here? Who's using Postgres? If you have a look at these two files, you will switch to Postgres, I guess. The parser of MySQL is a big, big mess. I will not use MySQL anymore because I guess there's so much people fooling around with that code. So I also had a look at Postgres. And if you are I'm not a C programmer, I have to admit. I just do everything in Java. So it was kind of hard to read through all the SQL C code. But compared to MySQL, Postgres was like heaven. It was like almost a pure joy just walking through the code because it's well documented, well structured, and it had a really cool and clean design, documented and perfect. So that was this. For me, this is just a far better choice. There's some somewhat, because I needed to have that in Java for hooking up with my machine learning libraries. So I was looking for some parsing stuff in Java. There's by Ingress, they have created a SQL parser collection, which is a tool set for a lot of different dialects like Oracle and so on. There's JSQL parser. This is a project of an Italian guy. I don't know the real name of. And basically, what I did for these experiments, I modified the JSQL parser to do some more parsing than the original has, and this is all available on GitHub. So, and also as well as the rest. So, if you have any interest in running that code, just contact me, and that's all open source. So that's it. That was my presentation, and feel free to have any questions. If you not do it right, then you're effective to what's called second order SQL injections. So just imagine a store procedure using values of your database. So you start a SQL, you create a stored procedure which does concatenate some of the values you have in some other table. So if an attacker is able to inject SQL commands into that other table, and your stored procedure is concatenating the values, that could just lead to another SQL injection. And that's called second order SQL injection. So if you manage to use like prepared statements to prevent the first case, then you're fine. So my approach would be to just have a look at every place where you where you use SQL and just stick to prepared statement. No, but if the stored procedure is relying on values you stored in the database, and these have not been properly stored, then you're infectable. Okay. Then thanks for attending, and if you have any more questions, just contact me afterwards.